Hello everyone, welcome to eSpace, a new lecture on Bootstrapped Amplifier. I'm Chandrachandran, MTech graduate from IC Bangalore, now working as senior engineer at Caltron. In this lecture, we'll be looking on, and so before getting into Bootstrapped Amplifier, we'll be looking on some basics, that is H parameter model, Miller's theorem, and then Darlington pair, self-biased Darlington amplifier, Bootstrapped Darlington circuit. About the lecture, it's a theoretical one. BTech level course, reference is integrated electronics, Millman Halkias. As a prerequisite, you should have a knowledge on basic mathematics, that is solving algebra, etc. like thing, network theory, solid state devices, basic electronics. This is just how amplifier works, like that. BJT amplifier, solid state device on BJT, and some network theory, which is Thevenin circuit and KCL, KVL, some basic stuff like that. And let us now start with H parameter model for common emitter amplifier. So consider simple BJT. This is a single BJT, simple BJT. It has a base, and this is a common emitter. Emitter is common to both input circuit. It's a two-port network. You can view as a two-port network. The input is a base and emitter section, and output is collector and emitter section. And emitter is common to both output and input circuit, so it is called common emitter amplifier. So let us go. So let us see, it's a two-port network. This is a C amplifier. Here, emitter is common to both sides. This is a base, input current IB, and again here output current IC, and emitter. VA is the input voltage, IA is the input current, V0 is the output voltage, I0 is the output current. So let us write as VA is equal to VA is a function of II and V0, and I0 is a function of IA and V0. So this can be written as VA is equal to this is a 2 by 2 matrix. This H parameters form a 2 by 2 matrix, and this equation is the input voltage equation, and this is the output current equation. That as a function of input current and output voltage. You can see here, and we have introduced some new constants like H11, H12, H21, and H22. So this is the equation for that. Just from this definition, we have written this equation. So again, with some modifications, we are writing this VA is equal to H11 is written as HI, and H12 is written as HR, and H21 is written as HF, H22 is written as HO. So this is the equation. This is a modified equation. VA is the input voltage, and IO is the output current. And this H parameter can be defined as follows: HI is equal to VI by I when VO equal to 0. That's the input resistance with output short. HR is the reverse voltage gain with input open. That is HR equal to VI by V0. If you can see that equation, we can get into this conclusions. HF is the IO by II, and when V0 equal to 0, that is forward current gain with output short, and HO equal to IO by VO when IA equal to 0, that is output admittance with input open. That is in ohm inverse, that is mho, MHO or Siemens. We can write it as mho or Siemens. So for a C amplifier, this is a circuit. This is a H parameter equivalent circuit. For a C amplifier, this is HIE and HRE VCE. That's a reverse voltage gain. This is a reverse voltage gain, and this is a forward current gain HFE IB, and this is the output conductance. That is HOE. 1 by HOE is the output resistance, and that's parameter for the same. So we can define in terms of base, emitter voltage, collector current, like that. We can define here VB is equal to HIE IB plus HRE VCE, and IC equal to HFE IB plus HOE VCE. So these are equations we should get remembered. You should remember these two equations. This is very important. And next one is Miller's theorem. So suppose we have a two-port network here. that is one is at the input it is vi v1 and ground, and at the output it is v2 and ground, and there is a i1 current flowing from input node to inside the network, and i2 from outside the network. Yeah, that's second port, that is at v2, this two second node. So I2 is flowing from output to input, and there is a resistor placed across V1 and V2, and where V2 by V1, that is the voltage gain at this across these two nodes is defined by K. If such a situation is there, so we can convert this circuit to two resistances from connected from one node to ground, and again here one node to ground, and these resistances are defined by z dash, that is z dash, it is z dash by 1 minus k, and z dash into k by 1 k minus 1, k by k minus 1, or otherwise 1 by 1 minus 1 by k. So the current I1 becomes, so we can derive these two equations here like this. The current I1 is equal to V1 minus V2 by Z dash, and this again becomes, we are substituting V2 as kV1, so this becomes V1 into 1 minus k by Z dash, and V1 by Z dash into 1 minus k, that is V1 by I1 equal to Z dash minus 1 minus k, and Z1, this impedance becomes Z1 equals Z dash by 1 minus k, and this is an important relation. This is equation 7, and current I2 equal to I2 is V2 minus V1 by Z dash, and thus again we have substituted here V1 equal to V2 by K, and that we have substituted, and we will get like this, and V2 by I2 K Z dash by K minus 1, and again it becomes Z2 equal to the output impedance becomes the output down the resistance where it is the node 2 to ground is connected, that resistance value is K into Z dash by K minus 1, or otherwise Z dash by 1 minus 1 by K. So inference, according to the gain of the amplifier, we can build high input resistance, negative resistance, or low impedance circuit. So we can here suppose if the gain of the amplifier is unity, that is K is equal to 1, then this Z2 and Z1 becomes infinity. That is the application in bootstrap bias circuit. We'll be looking on that in the next coming slides. And this is a Darlington pair. So let us find out the value of currents, and these are IB1, IB input current to the first transistor, and this is input current to the second transistor, and this is the output current from the last second transistor to the load. This is the output load, or we can connect here also the load, or this is the emitter resistance. So IB2 is equal to IE1 is IE1 equal to 1 plus beta into IB1. So IE2 equal to 1 plus beta into IB2. So 1 plus beta into IB2 can be, from this you can substitute here, that is 1 plus beta into IB1, that's equal to 1 plus beta the whole square IB1, 1 plus beta, and beta is very high, it is at the minimum range it will be 100. So plus 1 we can remove this 1 here, so I0 becomes beta square IB1, that's equation 9, beta square IB1. So suppose if beta is 100, then beta square becomes 10 raised to 4, that's a big value, so we are getting a big current gain at the output because of this Darlington pair. So we can also calculate input resistance. So here we will be using a simplified H model where only two H parameters are there, that is only the input resistance and the current gain, because the that's the reverse voltage gain value will be very less and can be ignored in many applications, and also the output resistance that will be very low, so we can ignore that. So this will be a simplified H model to calculate the input resistance. So you can here, from looking from the base of the second transistor, it is Ri2, that is Ri2 is a second input resistance, and this is Ri1 looking from the base of the first transistor, that is Ri1, and Ri2 equal to, you can calculate from here, Hi2 plus 1 plus HFE2 into Re. That is 1 plus, this can be ignored. This is approximately 1k, and this is into 100 into 10k, so it becomes a big value. So this can be, Hi2 can be ignored. So this we can write it as 1 plus HFE2 into Re. So this is the H model equivalent circuit to calculate the input resistance. This is IB1, IB2. This is a 2 H parameter of the transistor 1. This is a transistor 2. Q1, this is Q1, this is Q2, and this is the output current IE2. This is VI, VO. So this Ri1 from the earlier equation we can write it as HI Ri1 equal to HI1 plus 1 plus HFE1 into Ri2, and Ri2 we can substitute here, that is 1 plus HFE2 into Re. So it becomes Ri equal to 1 plus HFE square Re. This is, so HFE can be written as beta. Normally we used to represent HFE as beta. That's both are same, both are current gain of the transistor. So this becomes Ri equal to 1 plus beta square into Re, or otherwise beta square Re. Re will be in the range of 10k or so. So if from this 10 raised to 4 and this becomes 10 raised to 6 and more than that, so it's a very high resistance in the range of megohm. And we can also calculate the voltage gain from here. This is V0 equal to, the method is first calculate VO, that is IE2 into Re, and then calculate VA. VA is equal to IB1 to HIE1. You can use the KVL equation. From KVL you can write it like this: IB1 into HIE1, IB2 into HIE2 plus IE2 into Re, and substituting the values, IB1 equal to IE2 by beta square and IB2 equal to beta into IB1. Can write like IE2 by beta, you can write like this, and substituting here can get like this. And finally by rearranging we can get V0 by VA equal to R into beta square by HIE plus beta HIE plus beta square RE, and can be finally written like this: AV equal to V0 by VI is the AV, voltage gain AV is equal to RE by HIE by beta square plus HIE by beta plus RE. Typical value of HIE is 1k, and 1k by 10 raised to 4, that's a very low value. So we can ignore this term. And HIE by beta, HIE is in the 1 kilo, and by 100, that also it will be 1. So we 1 not 10, that can be ignored, and RE is in the range of 10, and Re by Re becomes AV is equal to 1, and it's almost equal to 1. So the voltage gain is unity here for a Darlington amplifier. So, and this is the practical circuit that the analysis we made earlier was a for a two transistors coupled like this Darlington circuit. In a practical circuit there will be a DC biasing to, for the transistor to the amplifier signal, there should be a DC biasing. So this is a DC biasing. There's a self-biased circuit R1 and R2, and this is a Re emitter resistor from where the output is taken. This is a DC coupling capacitor where to couple with the biasing and the input signal. So this is a self-biased Darlington circuit. So let us analyze the input resistance and voltage gain. Only the input resistance or the voltage gain of the self-biased. So this is a small signal analysis of the circuit where VCC, this is a VCC here. The VCC is made as short circuit, and all the coupling capacitors are short circuited, and this R1 and R2 becomes a parallel combination and comes like this. This Ri1 where it's the input resistance seen from the first base of the first transistor Q1, and this is the Ri is the input resistance seen from the input to the circuit. So this is the input resistance looking from the base of the Q1, that is Ri1. It is given as in equation 10, that is Ri1 equal to 1 plus betas the whole square Re. So the input resistance of the Darlington with self bias is, you can Ri is become Ri1 parallel to RB, where RB is the parallel combination of R1 and R2. So here Ri1 is in the range of megohm. This is the equation we have got from the earlier analysis, that is this one. So Ri1 is in the range of megohm and Rb is in the range of kiloohm. So in parallel when in parallel combination comes, it will result in less than in the range of kiloohm. So that's the drawback of the circuit. The input resistor is lesser and cannot be used in impedance matching applications, all as voltage opposed as told earlier, because usually the Darlington pair is used to match impedance, used in impedance matching applications or as voltage, but this circuit cannot be practically implemented like that. So to solve this drawback, we are using bootstrap biasing for the Darlington pair. So this is a bootstrap Darlington circuit. Here you see there's a R3 resistor connecting like this and a capacitance shorting from capacitor which connects from the junction of R1 and R2 to the output side. And this is the coupling capacitor here. This is the input is given to the base of the Q1 and output is taken from the emitter of Q2 through C2. C2 is a coupling capacitor, the output coupling capacitor, and C1 is the input coupling capacitor, and C3 is the parallel capacitance to in order to bootstrap the circuit. So this is a small scale analysis of the bootstrap amplifier, where VCC is shorted to ground here and R1 and R2 comes in parallel and it comes parallel with RE because of the capacitor is shorted like this, and R3 is a resistor comes in which connected to input to output. So this is the Miller resistance here, where it is connected through input to output. All the other capacitors are shorted here for the small signal analysis. So this is a Miller resistance, and this resistance can be connected from, we can change that according to Miller's theorem. We can connect it from base to ground and then emitter to ground, emitter of the second transistor to ground. So we'll see that. So applying Miller's theorem to R3, we can get two resistors Rm and Rn, which is connected to, just as discussed before. This is a node 1 to ground and node 2 to ground, and this some emitter to ground, that is Rn and Rm. And Ri1 is the resistance seen from the base of the first transistor Q1 to the circuit, and Ri is the input resistance, effective input resistance seen from the input side. So let us calculate input resistance. Ri1 is similar to Darlington amplifier, that is instead of Re, we have the emitter, we have Re parallel with Rb and parallel with Rn. So Ri1 equal to 1 plus beta square into Re parallel Rb parallel Rn. So we apply Miller's theorem and two resistors at input and output, Rm and Rn, the values are, so Rm becomes, it is from the Miller's theorem equation, we have R3 by 1 minus AV, that is here AV is unity here for a Darlington pair, AV is unity, voltage gain is unity. So Rn equal to R3 by 1 minus 1 by AV, and both Rm and Rn equals to infinity. So the effective input resistance is Ri, that's equal to Ri1 parallel Rm. Rm, as told, it is infinity. Ri1 is in the range of megohm, so Ri becomes in the range of megohm. So the drawback of Darlington amplifier is solved by bootstrap biasing, where we have achieved high input resistance, and so this is the drawback of Darlington amplifier is solved, and we can have high current gain, unity voltage gain, and low output resistance. So the Darlington amplifier with bootstrap biasing can be used in applications where it is impedance matching is required, voltage buffer, and fast switching like in TTL circuits. So that's it. That's the end of the video. Please like and share the video, subscribe the channel, and if you have any doubts, mail me to chanch484@gmail.com, or if you have any comments, put in the comment section of the video. Thank you.